Most of us learn the same basic model of a volcano in elementary school, a tall, steep mountain with a crater at the summit. That classic cone shape is an accumulation of slag. It is the cooled lava, ash, and rocky debris piled up from previous, relatively minor geological leaks. To understand a supervolcano, we have to look miles underground. The trigger for a supereruption is a massive structural engineering failure deep beneath the crust. The core is the magma chamber, a vast pool of liquid rock. Intense mantle heat makes this magma less dense, generating a continuous upward buoyant force. The solid crust acts as an unyielding lid, constantly strained by the expanding liquid pushing against it. This is a dynamic, highly pressurized containment vessel, constantly searching for a structural weak point. The behavior of this trapped magma depends on fluid dynamics, specifically a property called viscosity, which is a fluid's physical resistance to flow. Volcanoes fed by basaltic magma contain a silica-poor, high-temperature liquid rock that is highly fluid and has low viscosity. In basaltic frustums, expanding gases easily bubble out of the liquid and escape, safely depressurizing the system through slow, oozing surface leaks. Instead, supervolcanoes run on a rhyolitic magma. This is a dense, silica-rich material that behaves just like wet, sticky concrete. The chemical makeup of the magma dictates the outcome. A low-viscosity fluid allows the Earth to vent safely, while a high-viscosity sludge creates a physical blockade. Inside that rhyolitic sludge, immense heat boils dissolved water and other gases, converting them into expanding bubbles of steam. Thick rhyolite acts as a physical cage, locking gas bubbles in place. The unvented steam's thermal energy becomes trapped kinetic energy, violently pushing against the surrounding rock. This trap multiplies across billions of microscopic bubbles, spanning a magma chamber dozens of kilometers wide. With zero venting capability, the entire system now functions as a sealed pressure vessel pushed to its structural limit. The breaking point arrives at the exact millisecond the upward pressure of the trapped gas exceeds the physical weight and integrity of the rock ceiling. Scientists measure the size of these structural failures using the Volcanic Explosivity Index, or VEI, a logarithmic scale for explosive eruptions. A VEI-8 is the maximum metric on this scale. It represents an event that ejects over 1,000 cubic kilometers of material. When the heavy, rigid crust finally fractures under the immense strain, the entire subterranean chamber experiences a massive, supersonic depressurization. Thousands of cubic kilometers of pulverized rock and magma reach the stratosphere as glass shards, blocking sunlight and dropping global temperatures. When we look back down to the surface, we see the physical scar left behind on the Earth's crust. This scar is a caldera. It is a massive, cauldron-like sinkhole that forms when the ground's surface loses its structural support and collapses vertically into the empty magma chamber. This collapsed void is so enormous that an entire modern island town comfortably exists inside its footprint, seen here after the Lake Toba eruption. The resulting pitch-black caldera void and ash-darkened sky stand as a permanent, quiet testament to the catastrophic and world-altering power of a supervolcanic detonation.